second lecture on vector coordinates. As I see, there are 38 people, not everybody yet. So I will save other things for later. So right now, let's deal with the vectors. I'm now closing my camera so that I can deal with the screen. And so let me just check the pen. It works. Hello, pen. White. Yes, it does. Okay. All right, so we can move on. And so, vector in the coordinates. Today we are going to talk about vector coordinates. Vector coordinates, well, are a little bit different from the point coordinates. However, let's start where we are here. Suppose we have a three-dimensional system of coordinates. The same works in 2 dimensions, but I thought I'd just start immediately with the 3 dimensions, because sometimes we need to sketch things. And these things might be, let's say, more difficult in 3 dimensions, but that's why we need to practice them more. So the origin of the coordinates O, and then we have the axis X, Y, Z. Let's remember one thing about the system of coordinates in the space. That is, the x-axis seems to come towards us out of the plane of, in this case, that would be the screen. So the plane of the screen contains the axis, the y-axis and the z-axis, and the x-axis is coming out of there towards us. So that will be the orientation. This is called the right-hand orientation because if you imagine that your thumb is x-axis and your other fingers are y-axis, then actually from your right hand palm up, the z-axis goes upwards. For instance, you could use this description. Another way of thinking of it is, let's say, in mathematics. If you remember, for example, from school, from trigonometry, the anti-clockwise direction is the positive direction. So going through the shortest distance from x to y to z to x. In the anti-clockwise direction, the geometrical positive direction of rotation, we go in this positive direction from x to y to z. And that's why, let's say, well, not why, but this kind of system is called the right-hand system, right-handed system of coordinates. And in fact, we generally use the right-hand system. Why is it like that? I can't really tell. It's simply the matter of agreement, the matter of convention. All the mathematicians of the world have agreed that the system is oriented like this in a right-handed way. If, for example, the z-axis would be going down, we would have a left-handed system, because even if we turned the system so that the z-axis is up again, we would have the opposite orientation. From x to y to z would go not anti-clockwise but clockwise. So we generally assume that the x-axis is coming towards us, and the y-axis to the right, and the z-axis is going upwards. So suppose we have a point somewhere in the 3-dimensional space, let's say the point P, and it's not in any plane, any of the coordinate planes, is perhaps not on any axis, because those are the simpler situations. So let's simply suppose that we have the point P somewhere in the space. We can, for example, project it downwards to the plane XY, to the XY plane. And so we have a projection on the x-axis, that would be x of the point P. We project it perpendicular to the y-axis, we have y of the point P. And now if we project it perpendicular to the z-axis, so how do we do this? How do we sketch it correctly? Notice the diagonal of this rectangle. Of course, it's supposed to be a rectangle. And then parallel to this diagonal, if we go parallel to this diagonal, we will reach the correct height, the correct coordinate on the z-axis. That's z of P. So we have the 3 coordinates of the point P. So x, P, y, P, z, P. For example, I will actually complete this, or actually I will give you another version of the same diagram a little bit later. But now if we think of a vector, let's make it something bright yellow, for example. If we think of the vector, let's say OP, my sketching, okay, it's bad because it's a bit difficult as always to get where I want to get on the very perfectly black tablet. Okay, let's see. Okay, I'm going in the right direction. This is the vector OP. This is the vector OP. And we can say that at the moment, the point P is projected downwards on the XY axis. So we can actually read the X and Y coordinate there. And then if we project it again in a right angle against the Z axis, we find the Z coordinate like this. Another good way of finding the coordinates is imagining a parallelepiped, a cuboid, whose diagonal is OP. In other words, imagine something like a box, like a shoebox, such that the diagonal is actually the vector OP. Let me get another, let's make it, okay, I will choose a different color. Let's make it light blue. So, for example, if we, okay, what's that? I don't want this. If we actually try to build this box, that would be going up the same distance, going up from the point here and going then towards the Z axis, like there. You can imagine this box. You can imagine this box. It might be a cube, it might be not a cube, any other cuboid, a right-angled parallelepiped like this. So if you can build this box in the corner of the room, like in the corner of created by the three coordinate axes, then the main diagonal, the diagonal from the origin to the exactly diagonally opposite vertex of this would be the vector OP. So in principle, if you need to find the coordinates of any point P in 3 dimensions, the best idea might be just sketching this box, this perfect right parallelepiped, this cuboid. At the moment, this one looks like a cube. It's not meant to be a cube. It's just very approximate sketch. But we can at least think of it as this particular box. So this is a slightly better one, which I drew on paper and then take a photograph and then, I scanned it and then I pasted it in here. So the situation, the idea is generally the same. So what I did not do here was this diagonal, which is of course parallel to this diagonal of the base rectangle, so that we can check that all things are in order, that everything is matching and fixed. So this box, actually, the edges, the lengths of the edges of this box are actually equal to the coordinates of the point P, if everything is positive, of course. It might be that we go in the negative direction of one or more axes. Then, of course, we have negative coordinates, naturally. But in principle, the easiest way of thinking of coordinates of a point is thinking of a box and the diagonal of this box. Now, if we think not just about the point P, but the whole vector OP, we can actually imagine one thing. We can imagine that going from O to P, remember last time when we spoke about vectors, I mentioned this idea that we can actually express one vector through other vectors if we simply follow a certain route along those given vectors so that the endpoint and the starting point is clear. In other words, if I want to go from O to P following the directions of axis, I could say I go, according, first of all, this vector along the x-axis, then I go in the direction of the y-axis the correct distance, the correct direction, and then finally I go the correct distance in the along in the direction of y-axis, like this. So in principle, I could say that my vector OP can be written as the sum of the three green vectors, for example, OA, AB, BP. So I can actually say that the vector OP is actually vector OA plus vector AB, doesn't matter where A is, plus BP. Again, the points A and B don't matter. This would be true for any points A and B. But we choose points A and B so that we can move along the edges of the box. In other words, purely in the directions of the three axes of coordinates. And interestingly enough, this is how we will define the coordinates of a vector then. So it's the same picture now again from the scan. More or less, I haven't put the letters A and B there. So we see that, let's remember one thing. We had something called base unit vectors. I already mentioned they were the first unit vectors we actually encountered. We mentioned unit vectors. I mentioned unit vectors and I said the most famous unit vectors are actually the vectors that are in the direction of the axis. So the unit vector I on the x-axis, the unit vector j on the y-axis, and the unit vector k on the z-axis. Let's do it this way. So a rather simple base system. So what this means, denoted I, J, and K vectors. Many of you are already familiar with these, and you are familiar with the I, J, K notation for writing down vectors. So now in this case, what we can see here is that the xp, the coordinate of the x coordinate of the point P is the length. In this case, if it's positive, it's the length in the x-axis, the x component. So I could say x as a number times the unit vector I, because a unit vector would be only 1 unit long here. But if I multiply by the xp coordinate, the length, then I know that I'm going in this direction. If the x coordinate of the point P happens to be negative there on the negative x-axis, then of course we multiply the vector unit vector I by the negative number xp. Similarly, so we move along the vector OA, that is this vector, unit vector I times the actual correct length, seeing also the positive or negative direction. Then AB, it's the same as this vector here. So that would be the y coordinate of point P, lengthwise, positive or negative, negative if we are going in the opposite direction, multiplied by the unit vector J. So, for example, we could have 3 unit vectors I, 4 unit vectors J, plus some number of unit vectors K in the Z direction. For example, if the coordinates of the point P are, let's say, 2, 3, 4, for example, let's just take an example. So if the coordinates of P are 2, 3, 4, it means that we have 2 on the z-axis. We would have 1, 2, 3 on the y-axis, and we would have 4. Let's say 1, 2, 3, 4 on the z-axis. So this would become then, we move 1 unit vector I, 2 unit vector I. So 2i plus now 3 units in the direction j. So it will be 3 unit vectors j. Okay, that would be 1, 2, 3 of them. And then we would have 4 unit vectors k going 1, 2, 3, 4 in the positive direction, so plus 4 unit vectors k, which actually means that these numbers, 2, 3, 4, are the coordinates of the point P. And we can also call them the coordinates of the vector OP. The coordinates of the vector OP are defined as the coordinates of its endpoint, if the starting point, of course, is at the origin, not in other situations. But if the vector starts at the origin, okay, welcome all those people who show up late. We can use the vector coordinate, the point coordinates, if they are negative. We understand that simply those unit vectors are, of course, multiplied by a negative number. So we get a vector, the component that is going in the negative direction. But we also call this the coordinates of the vector OP. So in other words, the coordinates of the endpoint are the same as the coordinates of the vector, if the vector starts at the origin. If the vector starts somewhere else, we will have to discuss that separately. But if the vector starts at the origin, it's obvious that the endpoint coordinates are the same as what we will call vector coordinates. So the coordinates of a vector, generally, we saw this. OP equals XPI plus YPJ plus ZPK. That's the same thing from the previous screen. And if we talk about vector, we use a little bit different notation. It's only the matter of notation. So if we talk about vector coordinates, we don't use point coordinates. We call them vector coordinates or vector projections, actually, on the axis. And we call them AX. AY and AZ. And the next is how we denote them. If we write the vector horizontally, we generally write them in these spiky angular brackets, in these angular parentheses, so spiky or triangular brackets for the vector coordinate. So that if I write, for example, 2, 3, 4, I generally understand these are the coordinates of a point. But if I write 2, 3, 4 in these angular brackets, I understand that these are actually coordinates, the coordinates of some vector, So simply using different kind of parentheses, we can denote, we can indicate if we are talking about point or about a vector.
Miss.
What? Yes.
Professor, if you repeat it again about the bracket.
Yes. It will be quite important about the brackets, because if we talk about points, we use the round brackets always. If we talk about vectors, simply to tell the difference, because I could say, okay, I'll give you something called 2, 3, 4, and from the brackets you will know, am I talking about vectors or am I talking about points? And sometimes we also can write a vector vertically. So in principle, we can see that vector can be written as a column matrix. Or in this case, it's more like a row matrix, only we do put the commas, we separate the coordinates by commas so that we don't get confused, because sometimes writing in a hurry, it's very easy to not understand, not leave enough space large enough between the two coordinates to understand where one coordinate ends and the next one begins. So in principle, we can see that this is actually a row matrix. And evidently, there will be quite a few properties that will be similar to the matrix properties. Vectors and matrices are in fact connected. They are in fact linked and connected. And the basic interpretation, vector as a column matrix or as a row matrix, works very nicely. And in principle, what we do, the difference from matrices, with matrices, it was strictly stated, this is a column matrix, this is a row matrix. A vector, the same vector, can be written in both ways. So a matrix is strictly row or column. But if we talk vectors, basically, I mean the same vector. The same vector thus can be written as 2, 3, 4, using as the row notation with these broken triangular brackets. It can be written as a column matrix, 2, 3, 4 vertically, and it can be written as, let's say, using the base unit vectors, 2i plus 3j plus 4k. Same vector, 3 different ways of writing it down. Each way of writing it down has its own, let's say, benefits for certain situations. Generally, the least useful is this last one, using IJK vectors. I know that this is a very widespread system of writing things down, and base unit vectors are, in fact, important things. But for practical purposes, for things that we do with vectors, in most cases, this IJK notation is the least convenient. It really is inconvenient. It's much more convenient writing the vector horizontally or vertically as a row or column matrix. Yes, there is one situation where this IJK notation is good. One thing that it explains very nicely, but in the rest of cases, basically we use the column notation or the row notation depending on what is more convenient for us. What is more convenient for us? So this is the good thing with vectors. We can choose how to write the vector down in the manner that is most comfortable, most convenient, most efficient for us. Basically, this third way is the least convenient because it takes a lot of writing. It's not just write down 3 numbers. It's also write down 3 letters and write 3 arrows. So in fact, this is the least convenient. More preferable are the row or the column notations. But that's just about the notation. We will deal with that. Well, you will see how we use it as we use these notations in practice, in problem solving. And so, oh yes, now I have to erase my some things here. Erase this. Because evidently what this means is the vector I has coordinates 1, 0, 0, because the endpoint of the vector I would be at the point 1 on x-axis, as you know. The vector j is actually 0, 1, 0, because the endpoint of j lies on the y-axis at the point 1, and the vector k has coordinates 0, 0, 1 in a similar way. Also, we could notice that if a coordinate of a vector is 0, this means the vector is not going out from the plane determined by the other 2 axes. So in this case, if 2 coordinates of a vector, any vector, are zeros, so if any vector has 2 0 coordinates, it means this vector is going in the direction of one axis only. It's not moving off the axis. If a vector has 1 0 coordinate, it's evidently not moving out of one plane of coordinates. It's not, for example, if we have, let's say, vector, let me get color white. Suppose we have vector 2, minus 1, 0. In this case, we see that x coordinate is 2, y coordinate is minus 1, but it doesn't go in the z direction at all. This vector does not move out. It doesn't go out of the base plane of the plane xy plane. It doesn't go in the z direction at all. So by looking at these 0 coordinates, sometimes we can actually imagine the direction of the vector. 54. Somebody came very, very late, it seems. Almost half an hour late. Well, suffer the consequences. And so, let's move on. The magnitude of a vector. Let's start with a vector in 2 coordinates. Let's suppose we have a vector whose coordinates are known. The length let's say, coordinates. I'm going in two coordinates at the moment. So x and y, and let's suppose we have this vector. Okay, let it be OP. Who cares? So we have the coordinate of this vector. Let's say this is actually the vector A. So we have the vector coordinate AX and the y coordinate, the vector coordinate AY, which basically means because we have a right-angled, normal, regular system of coordinates, we have a right triangle. And the magnitude of a vector, remember in geometry, geometrically speaking, it is actually the length. It's the length of a vector. So how do we find the length of this vector? Of course, using the Pythagorean theorem. The length of the leg parallel to the x-axis and the length of the leg parallel to the y-axis. On the x-axis, we have AX. On the y-axis, we have this length. And of course, by the Pythagorean theorem, we can see that, how to erase this? Eraser. Back to pen. In fact, if I want to write OP magnitude or length, we know is geometrically, then according to the Pythagorean theorem, it is the length of the hypotenuse is the square root of the sum of the squares of the legs. And in this case, you can see it doesn't really matter whether the coordinates are positive or negative, because, for example, if we have one or both coordinates negative, for example, like this, we have AX, which is a negative number, for instance, when we square the length is positive, and when we square, we will have a positive number. It doesn't matter whether the coordinates of the vector are positive or negative numbers. When we square them, we get positive numbers. So we can use the Pythagorean theorem for the magnitude of vector in 2 dimensions. So if we have 2 dimensions, what happens in 3 dimensions? So this was in the plane. What happens in the space? Okay, I will now erase the unnecessary thing. That was this one. This was less necessary. And this is now also less necessary, as you can see, because we have it printed. And now let us see what happens when we have the space, 3 dimensions. In 3 dimensions, this is the previous picture. This is the first diagram, actually, and I can use it. I can use it to improve things a little bit. So I can say that this is now the AX coordinate, this is a Y coordinate, and this is a Z coordinate in 3 dimensions. The coordinates of the point of the endpoint is, of course, the same as coordinates of the vector. And what we see here, we actually get the same thing. For example, if I want to find the length of this diagonal in the base, let's say this small diagonal in the base of the rectangle, I know that in the base, the diagonal of this rectangle will be the square root of the AX square and AY square. So D would be the square root according to the Pythagorean theorem from this triangle, right? But we need the square because now I see that OP squared should be D squared, this segment squared, plus height squared, because we know that we have a right angle here. The vectors, the base vectors form right angles. So plus the Z coordinate squared. In fact, what we get this way is that we have the same thing as the Pythagorean theorem. We generally could say that this is the generalized Pythagorean theorem for 3 dimensions. The situation is exactly the same, only it's not a hypotenuse of a single triangle. In this case, it is the diagonal of the box, the diagonal of the parallelepiped, of the right parallelepiped, of the cuboid. But basically, the rule is exactly the same. So we can say we have this generalized Pythagorean theorem. Generalized Pythagorean theorem. And we can find the magnitude or the length of the vector normally using the Pythagorean theorem all in one piece. Now what next? Coordinates as projections. Coordinates as projections. So again, let's suppose we have this system of coordinates and a vector A. In this case, I drew it going downwards like this. And suppose that the vector A forms these angles, the angle alpha with the x-axis, the angle alpha between the vector and the x-axis. So this is the x-axis, and here we see the vector, the angle alpha. Now the angle beta with the y-axis, the angle beta with the y-axis, and the angle gamma. Okay. The angle gamma written like this, the angle gamma with the z-axis. Let's suppose we have this vector forming three angles with the axis. In that case, we can actually imagine that we can project this vector, the vector projections. Do you remember what vector projections were? We projected the vector to an axis, a line, perpendicular to that line, and we said, all right, the length of this projection with the plus sign if it goes in the same direction as the axis, and with a minus sign if it goes in the opposite direction. In principle, if you remember, then the projection actually could also, here we have the same picture, only all three projections have been drawn. So here it's a little bit more difficult to see the projection towards the z-axis. This one. So we are projecting, and this number would be the projection. It's negative because you see the angle between the y, why have I done this? This was y, this was z. This is y, and this is z, of course. I don't know why I wrote something wrong there. So basically we have vector projections. It seems that vector coordinates are actually vector projections. And the vector projections, if you remember, the vector projection was length of vector times cosine of the angle between the line and the vector. So in principle, we see that, first of all, vector coordinates are actually the projections of this vector on the axis. Secondly, remembering from the first lecture what a projection of a vector is. It's the magnitude, the length of this vector, times the cosine of the corresponding angle. So in principle, if we have the coordinates of a vector, we can find those angles this vector forms with all three axes. We have the angles this vector forms with all three axes, with each of these axes. All we have to do is, first of all, we need to find the magnitude by the formula from the previous screen. And we know the coordinates. If we know the magnitude, we can express these cosines, we can express these angles from there. So there's a new interpretation, a new idea about the vector coordinates. The vector coordinates are actually projections on the axis. Or sometimes we call them simply components. The vector component in x direction, the vector component in the y direction, the vector component in the z direction, because it actually indicates how far do we need to go in the three main directions in order to reach the endpoint from the starting point. So these are called the direction cosines. And so this is the same the same thing that was written on the previous screen. It's a repetition. You don't have to copy this. I'm simply putting it there to remind you. It was there. See, it was there, and I'm now putting it on the screen again. And so let's see. Then I can express all these cosines. I can write cosine alpha is coordinate, x coordinate divided by magnitude. Cosine beta is y coordinate of the vector divided by magnitude. Cosine of gamma is the z coordinate divided by magnitude of vector. And these are the cosines, remember, of the angles the vector forms with axes. And these are called the direction cosines, where the angles themselves can be called direction angles. But what is more important is direction cosines. Direction cosines are more important than the angles themselves, it turns out, strangely enough. So if we consider now this is another, it's another story, but it's simply to help us see what is going on. So suppose we have, let me just get the white chalk. That's actually a slightly fatter line, it seems. So let's suppose we have a unit vector in the same direction. So we have a vector A, and we have a unit vector A, let's call it A0, the unit vector whose length is exactly 1 unit. Whose length is exactly 1 unit. So the length is 1 unit for that vector, but if the direction is the same, the angles alpha, beta, gamma are the same. But then the coordinates, see, if we divide by the length of the vector, the number of the units inside that vector, we generally get a vector that many times shorter. We get the unit vector. So these are actually the coordinates of the unit vector. So the unit vector has coordinates expressly pure direction cosines. In other words, the vector A has coordinates a bit greater, perhaps, or smaller, depends, multiplied by the length. How many units is the length of this vector? So remember vector multiplication, we take this unit vector, multiply by the number of units, that would be the length, and we get that many times longer, that we get the actual vector A. So the unit vector has coordinates that are already clear, pure direction cosines. The vector A itself will have coordinates absolute value of A, magnitude of A times cosine alpha from this magnitude of the vector times cosine beta and magnitude of the vector times cosine of gamma. So these, see, the coordinates of the full vector are these numbers. But if we only take the unit vector, which is shorter, we only have those cosines. The cosines are the coordinates of the unit vector. But we also know one very interesting thing. We also know that the unit vector has length 1. We also know how to find that length. of the unit vector. That is according to the Pythagorean theorem. It's the square root of the sum of the squares of its coordinates. So what this means is that the sum of the squares, well, I could put 1 squared. I could put the square here. But it doesn't matter because 1 is 1 anyway. The unit vector has length 1. Therefore, we have 1 squared, which is still 1. The coordinates are cosine alpha, cosine beta, cosine gamma. And we know that we can find the magnitude of the vector, the length of the vector, if we add all the squares of coordinates and take the square root. But in this case, I'm not even interested in the square root. What I see is that evidently any vector will have this correspondence. That is, the sum of the squares of all 3 direction cosines equals 1. And that would be something very important for our purposes. This will be something very important. So we get this idea from the unit vector But this is true for all vectors, because remember, okay, the unit vector has length 1 unit, but any vector in the same direction, that is, having the same alpha, beta, gamma, will also have this property. The sum of the direction vector squares of a vector will always be 1, which means if I know 2 cosines, if I have 2 direction cosines, then I can find the third direction cosine, maybe with an accuracy to the magnitude. It could be plus or minus, depends on other knowledge, other information that we might have. So these alpha, beta, gamma, let me remind you, these are the 3 angles that actually define the direction of a vector in the system of coordinates. You could think of it, let's go back. You could think of these 3 angles as, let's say, perhaps three strings that hold the vector in the correct direction, in the correct space. You could imagine something similar if you put up a pole, vertical pole, and then you use 3 strings to keep it perfectly vertical. You use 3 strings to the ground in 3 different directions. This is something similar, only it deals with angles. So we have the vector A, and then these 3 angles are the 3 values, 3 numbers that hold this vector in the correct direction. So these 3 angles, alpha, beta, gamma, or rather the cosines of these 3 angles, are the 3 numbers that actually keep the vector in the correct direction. Keep the vector put in or rather, they help us understand the correct direction of the vector. Okay. Okay, now vector coordinates from 2 points. Let's start by supposing that we have a vector somewhere else. Oh, no, actually, we'll be drawing it. Okay, doesn't matter. Okay, so for example, I have the vector from point P to, oh no, I will take vector not P, because P we generally use in a different sense. I will take vector from point M to point, let's say, N. And we want to know the coordinates of such a vector. Can we only find the coordinates of a vector that starts at the origin? Okay, 2 people have lost us, as far as I can see. Coming and going, fun. And so what we see is we have the same vector. I take the vector Mn. Remember, our vectors are free. I can take the vector Mn and put it at the origin. Let it start at the origin. In other words, I could say that the vector OP, if it's put in the origin, suppose it's exactly the same as the vector Mn. So that means the same direction, it means the same length, same magnitude, everything is the same. So let's remember what the coordinates of the vector OP actually are. What do they mean? They mean the projections on the axes, x and y, so that we get the correct components, we get the right triangle. So in the same way, I can construct the very same right triangle for the vector Mn. Of course, it's a little bit hanging in the space. It's not not close to the origin, it's not close to the axis perhaps, but the triangle is exactly the same, because we have the same length and same direction of hypotenuse and the same directions of the angles. It's the same. So basically, I would say that this should be the same component as this. So this should be AY, and this, let's put here M and K, for example, MK is actually the same component as this. So all we have to do is understand how to deal with the coordinates of M and N to find these components. Remember that we still see, okay, if I go clearly horizontally from point M, I will get the projection of Mn on the x-axis because it's the same. It's the same. We can see it here, and we understand it will be the same length. It will be the same number. Positive or negative depends on the direction of the vector. So basically what we need to see is understanding how to find the vector coordinates from one point to the other point. And we can think...
So we could just minus OK and OM, right? To get MK.
Wait. You shouted so suddenly that I didn't quite catch you. So basically what we need to do, we need to subtract the corresponding coordinates. We need to find the distance NK and MK. And so finding the coordinates of the vector would take finding this horizontal distance and finding this vertical distance. So supposing we have three coordinate system, basically the same thing happens. So in order, if the 2 points are given, so let's see, AX, we get subtracting from the nx coordinate, subtracting the x coordinate of M. This distance is actually the difference of these two numbers. So here we have xn minus xm, that would be this projection. And similarly, we would have yn minus ym, that would be this projection if we find the difference of the y coordinates. If actually the vector is going in another direction, downwards or backwards, it might happen that the endpoint coordinates are smaller, less than the starting point coordinates. So this might give us negative vector coordinates, but that's all perfectly fine. So in this case, we would see that the vector AB has coordinates differences, the difference of the coordinates of the endpoint and the starting point. Endpoint coordinates minus starting point coordinates. It can also be explained in a different way. It can also be explained, for example, suppose we have the origin of coordinates O somewhere. So we have vector OA and vector OB. And then let's just remember that if I subtract vector OB minus OA, I actually get the vector AB. Remember, subtraction of vectors, we go from the second vector endpoint to the first vector endpoint. So to get vector AB, I have to subtract the OB minus OA vector. Again, an indication that we have to subtract the coordinates endpoint minus coordinates starting point. Always endpoint minus starting point. So this means that this vector AB, this particular vector in our case, we could say, all right, the vector AB is, we could subtract, for example, I will use the vertical notation, the vector B coordinates 1, 4, minus 2, and then subtract the A coordinates 2, minus 3 means we add 3 and subtract 8. And so we have minus 1, we have 7, and we have minus 2, minus 8, that's minus 10. And that would be the coordinates of AB. So subtracting the coordinates of B minus A. From B, subtract A coordinates. Or sometimes it's actually easy to just compare the values of the coordinates and think, okay, in X direction, going from 2 to 1 means going minus 1. In the Y direction, going from minus 3 to 4 means going plus 7. And in the Z direction, going from 8 to minus 2 means going minus 10 steps. So we can also think this way. But what we have to remember is that it's always end minus start. End point coordinates minus start point coordinates. Let's see. All right, we have exactly the same now printed. So I will again use the eraser to get rid of my scribbles so that you see things that, as they are printed, like this. So end minus start, end minus beginning, but that is only to find the coordinates of a vector. And remember that what this actually means, these coordinates are components. This is what we go this is what we go in the x direction. This is what we go component in the y direction. This is the component in the z direction. Yes, one or more of these could be negative, or one or more of these could be also zero. Anything could happen as long as we remember that it's always coordinates of B minus coordinates of A, coordinate of B minus coordinate of A, coordinate of end minus coordinate of start. That's the important thing for this, for the vector coordinates. It goes, let's say, sometimes it goes against our intuition. Sometimes that might happen, that it goes on against our intuition. But in general, this is how it works. So I am not exactly clear where the minuses extra came from. Probably something remaining from the previous thing. All right. So now vector operations. Why do we need vector coordinates? So that, of course, we can use more algebra, than geometry, of course. So for vector multiplication by a number, remember it's called scalar multiple because a number, as opposed to vector, has a specific name, a scalar, to stress that it's just a number. So a scalar multiple means vector times number. We already went through this last week. And now if we have a vector in coordinates, so what happens when we take a vector multiplied by a number? Of course, like in matrix algebra, if we multiply a row matrix by a number, we get a new row matrix where all elements are multiplied by that number. So this is where the idea that a vector is actually a row matrix or a vector is actually a column matrix is very useful, because that makes us understand very easily how to deal with some vector operations. So this fits very, very nicely with matrix algebra. And also there are some things with the scalar multiples. Remember, the opposite vector has opposite coordinates. So in principle, for example, if you have vector AB, for example, having coordinates, let's say 2, -3, and 1, then the vector BA is the opposite vector, is opposite to vector AB, and it has coordinates -2, 3, -1. So it's very easy. If you have a vector computed, writing the opposite vector is very, very easy. Simply change the signs of the coordinates. You don't have to compute it fresh from their points. So that's opposite vector. That's very, very useful for practical purposes when we do the computations with the vectors. All right. Now, checking for collinearity. Remember, we had this idea in geometric interpretation that two vectors are collinear, that is parallel to the same line, if and only if one of them can be written as a number times the other vector. So if this is A, then this is K times A, and so is the vector B, for example. So if I have two collinear vectors A and B, then I can have no doubts that such number K exists. For two collinear vectors, such a number must exist. But what to do with coordinates? What to do with coordinates? So this is the same thing that I just said. I have just written it down. So two vectors are collinear if and only if there exists some non-zero number, scalar k, such that k times vector A is B. exactly the same thing that I just explained, and I rather reminded you, because we already discussed this, we already had it last week. And now, corresponding coordinates are proportional, because what we see, if one vector A is AX, AY, AZ, the three coordinates of this vector, and the second vector is collinear. This means that the second vector can be written like this. What we see, this is the bracket. What we see is that the ratio of the coordinates is the same. This is why we say the corresponding coordinates are proportional. So the x-coordinate of A, the ratio of x-coordinate of A to x-coordinate of B is the same as the ratio of the y-coordinate of A to y-coordinate of B. So x-coordinates, ratio of the x-coordinates is the same as the ratio of the y-coordinates, is the same as the ratio of the z-coordinates. So if you have two vectors, you can actually check whether they are actually collinear. So for example, we could say if I have a vector, let's say if this is the vector A, for instance, and then we have a vector B that has coordinates, let's say 12 minus 18, 6. Then I can say, yes, okay, to the ratio 2 to 12, the ratio of the y-coordinates minus 3 to minus 18, the ratio of z-coordinates 1 to 6. These ratios are exactly the same. So I would say, yes, I check and I say, yes, the vector A is indeed collinear to the vector B. If even one of these ratios is not the same as the other two, then we say, no, these two vectors are not collinear. So this is a very important test for collinearity. This is the easiest way for checking whether two vectors are parallel or not. Because if you have three-dimensional situation, it's very difficult to imagine. It's very difficult to sketch in 2 dimensions. And even if you have an opportunity, if you have, let's say, a software like GeoGebra or any other software that allows you to rotate the image 3-dimensionally, it's rather difficult to see whether the two vectors are collinear or not. So if you use coordinates, you will know for sure, precisely and accurately, comparing the coordinates of two vectors, rather writing the ratios and checking the ratios will give you the precise and ideal answer. So you will always know whether two vectors are collinear or not. If they are collinear, then these three ratios must, of course, be identical. What else? Sum and difference of two vectors. If we add or subtract vectors, again, something that most of you probably remember from school, we actually add or subtract their corresponding coordinates. If we have two vectors, A with coordinates and B with coordinates, what we have is, of course, simply the sum or the difference of those coordinates. We can prove it very easily. We can prove it using those IJK vectors. And this is one of those moments when those IJK unit vectors are actually very useful. You could say AX I plus AYJ plus AZK, and then we are adding the B vector BXI plus BYJ plus BZK. And now if we combine the vectors, which we know from vector algebra, it is allowed, we can do that. From matrix algebra as well, we could say, okay, now the new coordinate, new number multiplied by I algebraically is AX plus BX times I plus, and so on and so on. The same thing for J and K. So in principle, it's very easy to understand why this is so. in practice, all you have to do is know what to do with those numbers. Simply understanding what has to be done with these numbers. So you can do these things with coordinates, just like you did it with matrices. Remembering that vectors are actually row matrices, or maybe column matrices if you like to write things vertically. So in practice, you could write, for example, the vectors one below the other and add them just decently. For example, if we have a vector A, 2, minus 7, 0, and then the vector B, which is, for example, minus 1, 8 and 1, and then when you add these two vectors, it's actually very, very easy to do it horizontally, no problem at all. If you prefer to do things vertically, also possible, very similar. 2 and minus 1 is 1, minus 7 and 8 is 1, 0 and 1 is 1. Okay, I didn't set out to get this. It's an accident. I wasn't thinking at all about the sum that we might get. But if you need to add or subtract vectors, you could just as well write them one below the other, and you will see exactly what happens. In principle, a very simple thing. Distance between 2 points. So we get a lot of theory today. Distance between 2 points and the midpoint of a segment. The distance between 2 points, let's suppose we have point A and point B, and we need to find the distance between these 2 points. So what we can understand is, evidently, if we think of the vector AB, that is, the correct differences of the respective coordinates. So x2 minus x1, y2 minus y1, z2 minus z1 is the vector AB, and the distance between A and B is basically the same as the magnitude of the vector. It's the same as the magnitude of the vector AB. So that would actually be the square root of the sum of squares of the coordinates of this vector, or the squares of the differences of coordinates of the 2 points. So the distance, if we ever need to find the distance between 2 points, we have to subtract the coordinates of those points, the corresponding coordinates. We need to find the squares of those differences, add them up, and find the square root, just like we do find the length of a vector, the magnitude of a vector, because in principle it is exactly the same thing. Now we will discuss something else. So this is fairly simple from vectors, very, very simple thing coming from vectors, of course. Now, how to find the midpoint of a segment? Now, again, we will suppose that we have a segment with, let's say, A and B having the same coordinates, x1, y1, z1, and x2, y2, z2. Let's suppose we have the midpoint M, and we want to find the coordinates of midpoint. We want to find the coordinates of the midpoint. So what we might think is, suppose we have the vectors OA and OB. So this is the point O, origin. But we need to find the coordinates of the vector OM. At this moment, what I have to note, what I have to stress is that if we take the vector from the origin to any point, we call this vector OA the position vector of point A, position vector or radius vector of point A, because also it indicates the position of the point A, and the coordinates of vector OA are the same numbers as the coordinates of the point A. Vector OA has exactly the same coordinates. We simply normally write them slightly differently. We use the angular brackets, perhaps, or we write them vertically if we mean the vector. But the numbers are exactly the same. So if we think about the vectors OA and OB now, So we have the vector OA, we have the vector OB, and we want to find the vector OM, which will give us the coordinates of the point M. So let's just remember, how can we express the coordinates of point M using vectors OA and OB? Remember that expressing these things meant that we have to imagine a route, somehow a path from O to M using the given vectors. So there is a possibility of doing this algebraically like this. I can say that vector OM is vector OA plus vector AM. Yes, vector AM is unknown. That's true. So perhaps we could go from O to M differently. So let's go through point B. We can go OB plus BM. Again, BM is not something very good. But on the other hand, remember that M is the midpoint, which means vectors AM and BM are opposite vectors because they have the same length, same magnitude, half of AB, but opposite directions. So in principle, if I add up these, I get 2 times OM, adding up these equalities, and I have OA plus OB plus AM plus BM. And now we see that vector AM and vector BM are opposite vectors, which means their sum must be the zero vector, because opposite vectors, opposite coordinates. When we add the opposite coordinates, we evidently get 0, 0, 0. So the sum of opposite vectors is, of course, the zero vector. So it's like working with numbers. It's as if we are solving a system of equations in algebra. We are doing the same with vectors in some ways. And so we say, okay, the terms AM plus BM, they cancel each other out. It's like two opposite numbers canceling each other out. And so we see that the vector OM is 1/2 of vector OA plus OB. If we think in terms of vectors. Now let's remember that if we have a position vector, so if we have the position vector, the position vector of point M actually has the same coordinates as the point M. So the vector OM already gives us the coordinates of M. So from the vector OM, we can directly, it's not a vector. From the vector OM, we can directly find the coordinates of the point M. And understanding the operations OA plus OB, it means that I am adding up vectors OA and OB. Those vectors have the same coordinates. So I'm writing now here, vector OA has coordinates x1, y1, z1, the same as the point A. The vector OB, position vector of point B, has the same coordinates as the point B, and those would be x2, y2, z2, which means if I add these two vectors, OA plus OB, we get sorry. Okay, OA and OB. We have the sum of the coordinates, x1 plus x2. I apologize, I had an unexpected phone call. I denied it, I closed it. X1 plus x2, y1 plus y2, z1 plus z2, like this. And then half of this vector, 1/2, this means the vector OM is half of this vector. How do we do it? We do it by multiplying every coordinate by 1/2. Divided by 2, 1, 2, divided by 2. Like this. And so we have the formula for finding the coordinates of midpoint. If we know the coordinates of two endpoints of a segment, then we actually find the coordinates of a midpoint as the mean values, the average values of the endpoint coordinates. As simple as that. So supposing we have coordinates A and B known, we add them up in pairs, divide by 2, and we get the coordinates of the midpoint. Now I think I have to erase because, yes, you see what happens. I have written things all over my own screen. So now I have to erase all these things. This was an explanation of how we got this. But now the result. So again, see, we already had it written. I had it written. So this means half of the sums of the corresponding coordinates, which means the midpoint coordinates separately can be found from the endpoint coordinates as the average values of the two numbers. So if I know the coordinates of one end and of the other end, I add them up, divide by 2, and I get the coordinates of the midpoint. Okay, this is something that I somehow lost from the lecture file. I will actually introduce this idea back. I have somehow corrupted my lecture file, and I lost this part. I lost this midpoint part from the lecture file. It's not in the file, therefore it's doubly important until the moment when I can repair the file. I will do that. But this is something to be remembered, how to find the midpoint, because again, in the future, it comes in very, very useful in several situations. It's not always just, I want to find the midpoint. The idea of the midpoint is useful for other things as well. Now, the final idea for today, before we start some exercises, linear dependence. The linear dependence. Linear dependence of vectors is connected to the idea again of linear combination. Linear combination again is something that should be somewhat familiar to you. For example, if we have two vectors, vector A and vector B, then a linear combination of these two vectors could be a new vector. For example, 2A plus 3B is a new vector C, and we say, okay, C is a linear combination of A and B. We can multiply, we can find some numbers. In this case, for example, 2 and 3, so that from those two vectors, I can build my third vector, my new vector. In other words, a linear combination is simply the sum of vectors multiplied by some numbers. Just like we did with matrices and rows and determinants and rows. So a linear combination of the vector system, it doesn't have to be just two vectors, it could be n vectors. Each of these vectors, as you can see, is multiplied by a different number. C1 times vector A1 plus C2 constant 2 times vector A2, and so on and so on. So we have a vector system of n vectors. We multiply each of these n vectors by some number and add them all up. And then we say, okay, that's a linear combination. This looks long, but in fact, we generally combine two vectors to get a third vector or combine three vectors to get a fourth vector. In practice, we don't make bigger linear combinations. We don't need them. In principle, the most common thing is combining two vectors to get a third vector. We will also discuss this idea probably next time when we will have probably quite a lot of practice exercises. Quite a lot of practice exercises about vectors and vector coordinates and expressing vectors and so on. Because last time we only discussed the geometrical ideas about vectors, but there was no time for many exercises. So next time on Wednesday, we will do lots of exercises for the sake of practice. Now, linear dependence. Linear dependence. So what might be dependent on what? And it turns out that a vector system, again, the same vector system of n vectors, but we don't take 0 vectors, n vectors. We say it's a system. Let's suppose we have some vectors, n of them, and the system is called linearly dependent. So the system as such is linearly dependent, all of them together, is dependent as a system if one of the vectors can be expressed as a linear combination of the other vectors. In other words, if, for example, A1 can be written as constant C2 times vector A2, constant C3 times vector A3, plus and so on, constant Cn times vector An, for example. In this case, I have expressed the vector A1 as a linear combination of all the rest. In that case, if this is possible, we say linear dependence. We say the system is linearly dependent because the vector A1 sort of depends on the rest of them. It might be that I express the vector A2 or A3. In many cases, it doesn't matter which vector is expressed by which other vectors. But in principle, if we can express one of the vectors using the others, then it is dependent, because we see that one vector can be written in dependence of the others. And if it's not possible, then we say the system is independent. In other words, we say the vectors are mutually dependent or mutually independent. It's all about being together, how they act together. Independent, that means that not even one of these vectors can be expressed using the other vectors. Dependent means if I have a vector that can be expressed using the other vectors. And formally, it means, let's say, two non-collinear vectors. They are independent. Non-collinear vectors, that means they are not parallel. They are non-collinear like this, linearly independent, which means that, of course, I cannot express the vector A using the vector B. No way, because their directions are completely different. So they are independent because A and B, I cannot say A is number times B, because then they would be collinear. These are collinear, these are dependent. I can express one of these two new vectors using the other vector. I can write vector C is, so let's say vector C is half of vector D. For example, these vectors are collinear and they are dependent. These vectors are not collinear and I cannot express anything. I cannot find any number to multiply by A so that I get B, because they are not collinear. Remember, we had this property, this condition of collinearity, which stated if two vectors are collinear, then one can be expressed as number times other. So, of course, collinear vectors are dependent. Non-collinear vectors, two of them, are independent. But then there's another new interesting thing. Three vectors are linearly dependent only if they are in the same plane. In other words, what this means is that if I have two vectors in the same plane, I am now sketching, for example, two vectors in the same plane, and the third vector is going out of this plane. So that it's not in the same plane, it's going outside, for example, up, like this. So in principle, these are independent. These vectors are independent because the yellow vector is not in the same plane. It cannot be expressed using the white vectors. And of course, they are independent. They are dependent if they are in the same plane. In other words, again, if I have three vectors and they are in the same plane, which means perhaps I can start them at the same point, and they are still in the same plane, like this, they are dependent if they are in the same plane. Because this figure is flat now, and in principle, I can form a parallelogram, and then I can adjust some numbers, and I can express one vector with the other two, for example, if they are in the same plane. We will discuss exercises next time very, very seriously. They are important for Wednesday. And now, linearly dependent vectors, if and only if the determinant forms from their coordinates is 0. So now we see, again, a connection to matrix algebra, to linear algebra. Determinants. Not only vector is a row matrix or vector is a column matrix, but also now we get determinants to discuss vectors. Why is that? Why are the vectors linearly dependent if the determinant is 0? Again, a determinant is 0 if one row is a combination of the other two rows. In other words, if I can subtract, remember row operations, so that this last row becomes all zeros. Because they are dependent, because actually I took this last row and said, okay, let's add number k times first row, and let's also add number m times the second row, and then I get all zeros. That means determinant is 0, but this thing that we can add, other two vectors multiplied by numbers to obtain that 0, makes these dependent. So, for example, if row 3 is equal to, for example, 2 row 1 plus 7 row 2, for example, it basically means the same about these vectors. Vector C is 2 vectors A plus 7 vectors B. So this means dependent, and this means determinant is 0. Basically, it's the same thing written in two different ways, as rows or as vectors. If we use the idea about rows, we see that the determinant must be equal to 0. If we use this idea written as vectors, we say, okay, by definition, they are dependent. So the vectors are linearly dependent if and only if this determinant is 0. All right, so this is all about the theoretical part. We have a few minutes. We have 8 minutes. And we can have a look at some examples, some exercises.
I have a question.
Yes. Well, ask your question.
Yes. So I want to know if there's other or it need to be 3.
I lost you.
So for the dependence, right? So can
No, I keep losing you. I keep losing you. You're switching off your something is happening to your microphone.
my question is, if I want to know if there's need to be 3 vectors for it to be dependent, or it could be 2.
If 2 vectors are dependent, then they must be, as you see, they must be collinear, because this is the only thing. If one vector is a number times the other vector, then they must be collinear vectors. So yes, 2 vectors can be dependent. This simply means they are collinear. They can be dependent. Okay, so now points A and B, find coordinates, magnitude, and the unit vector in the same direction. So suppose we have point A with coordinates 4, -2, 5. And the point B with coordinates 1, 4, 3. And of course, yes, we have the vector AB. So the coordinates of the vector AB, as we already saw, it's very convenient, in fact, to write them vertically, because we then write 1, for 3 coordinates of the endpoint, then immediately minus, 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 and subtract the coordinates, now the coordinates of the starting point. 4 minus 2, 5. And we see 1 minus 4 is minus 3. 4 minus negative 2 is 6. And 3 minus 5 is minus 2. This is the vector AB. If you want, you can write it horizontally, minus 3, 6, minus 2. If you want, you can write it using minus 3 unit vector I plus 3 unit vector J minus 2 unit vector K. I would say, being very lazy, this last notation is the one that I don't like because it takes the most writing, too much writing. So we are all lazy, we don't like to write much. So let's use the notation that is official but does not require so much writing. Magnitude. Now the magnitude is the square root of the squares of all 3 coordinates. That would be 3 square plus 6 square plus 2 square. Of course, it doesn't matter that I wrote only positive numbers squared, because negative numbers squared is still positive. So we don't have to worry about the signs when we are finding the magnitude. And so we have 9, 36, and 4. 36 and 4 is 40, 49. So the magnitude is 7. The magnitude of this vector AB is 7, as we can see. It will not always be nice numbers. We will get irrational numbers, square roots of crazy numbers all the time, because it's not many vectors that can be found that they have nice numbers as magnitudes, as length. Now, the unit vector in the same direction. So I know that the magnitude of AB is 7. I also know that the vector AB itself, I have already written it up there. I will write it here. Minus 3, 6, minus 2. And its magnitude is 7. But now I need the unit vector AB0 in the same direction. That means this is 7 units long, and I need 1 unit long vector in the exact same direction. So imagine that you have 7 such units in the vector AB. How do we find this unit vector now? To make it 7 times shorter, of course, if AB is 7 units long, then the unit vector will be 7 times shorter, right? So what do we do to make it 7 times shorter? We have collinear vectors 7 times shorter. The magnitude must be 7 times less. But what we can actually do is simply multiply by 1/7. So the unit vector will evidently be 1/7 of the vector whose length is 7. So 1/7 of the vector minus 3, 6, minus 2. If I want the unit vector, that is minus 3 over 7, 6 over 7, minus 2 over 7. These are 7, 7, 7. And that is the unit vector. That is the unit vector. I don't have to, so we understand that if I want a vector 7 times shorter, remembering from geometry, I indeed have to multiply it by 1/7. That was geometrical interpretation of multiplication by number. But in coordinates, it means we do this with all the coordinates. And so the result turns out to be, let's say, rather simple. All we really need is the length. We need to know the magnitude, we need to know the coordinates, and we can produce a unit vector going in the same direction. That would be simple enough. Next, all right. Okay, I hope I can erase this first part because that was the very basic things. Now, vector A plus B. Let me check, 1 minute remaining. I want to finish this slide, and then next time we will do many exercises, but no new material yet. Because basically we have missed out on a lot of exercises. There was not OK from OM to get MK. I agree. We can subtract OK from OM to get MK. I agree with all this. The distance formula, but this is the distance formula. This is the distance formula. We got the distance formula, there we have it. Well, when we had it previously, it is the same. I'm simply demonstrating how the things are the same to what you already knew. And now this last exercise. So A plus B, we can write vector A is, I can write it horizontally, 2, 3 minus 6. Vector B is evidently I coordinate. The first coordinate is 0. For J, that means second coordinate is 4 and third coordinate is 3. So I can rewrite it in the matrix form. Now, A plus B, we see that A plus B will be add 2, 7, and minus 3. A minus B, subtracting A minus B, subtracting 2 minus 0 is 2, 3 minus 4 is minus 1, and minus 6 minus 3 is minus 9. Okay, this is finished, and this is finished. 2A minus 2B. Okay, I will write now vector 2A is 4, 6 minus 12. I was just looking at the vector A and doubling the coordinates. Minus 3B, all right, I'm writing vector 3B, it is 0, 4 times 3 is 12, 3 times 3 is 9, and now I have to subtract. So 2A minus 3B, just subtract 4 minus 0, 4, 6 minus 12 is minus 6, minus 12 minus 9 is minus 21. Magnitude of A, we have the same numbers as we already did. It's the square root of 2 squared plus 3 squared plus 6 squared. We just had these same numbers, only with different signs and different order. So it's still the square root of 49. The magnitude of B is evidently, first coordinate was 0, B is this vector. So 0 square plus 4 square plus 3 square. Evidently, these are the Pythagorean numbers 4 and 3. So this magnitude is 5. We can compute it. And the magnitude of vector A plus B. And the magnitude of vector A plus B is, no, it is not 12. You cannot add the two magnitudes. Because remember, if you have two vectors, the length of the sum is actually, it could be less than the sum of the two lengths. So the magnitude is not the sum of the both original magnitudes. We have to take the coordinates of vector A plus B. So it's 2 square, it's 7 square, and it's 9 square. Anything else would be incorrect. You have to take the actual coordinates of the vector. You cannot add 7 and 5. So it will be 4, 49, 81. 49 and 81 is 120, 130, and 4. So square root of 134. So this is the magnitude of the vector A plus B, which is not 12, it's less than 12, because 12 is square root of 144. So we can actually see also from the picture, I do think that at school you were taught this idea that if you have 3 points not on the same line, then the distance between any 2 points is less than the sum of the other two distances. So it would be a mistake to just directly add the two magnitudes. Okay, people. Now, how many of you are still here? Okay, some people are already lost. So probably those are the ones whom I would need to address here. So what you saw, yes, somebody, okay. Someone wants to ask something? Please ask. No, they won't. Don't want? Okay, that's an accident. So please, Friday's test showed one thing, how important it is to read instructions and to listen to instructions and to come on time. You saw that the main reason for you being split into 3 groups is so that I can manage a smaller number of students. I cannot manage 65 students at the same time, all the cameras on the same screen. So it is important that you actually, first of all, keep to your appointed time. Don't come too early. Okay, 5-10 minutes, that's okay to get ready for the test, but definitely not a half hour early or at another group's time. There was a certain reason why I actually assigned different times to different groups. That's one thing. Another thing is cameras. I'm absolutely not happy watching the top of your head. I need to see your hands and your face. And it was written, and I told you during the lectures. So next time I will simply throw out those people who do not comply with the requirements. If I throw you out of a Zoom meeting, you can't get back. Next thing. The naming of the files. So yes, okay, I understand that in the first time there was a mess, you hadn't practiced. You do need to practice to make those files. You missed the upload time, but then you had to email it to me. So exactly for those purposes, always you need to name the files with your name and the version number. I said it, I wrote it, it was indicated everywhere. You simply do not pay attention, or you are too late arriving and you miss the important parts. So please pay attention to what I say, pay attention to what is written in written form, and actually do read the course requirements in Ortus. I put all the information in Ortus, but there's about 2/3 who do read it and 1/3 of the group who does not read it. That's not acceptable, people. So I understand the first time it's as we are getting used to the idea, as we are setting things up, but in the future, please be very, very careful about how to do things properly. It's not because I just decided I wanted to do that. I wanted to do this way. It's because I need to organize the exam so that I can see everything, manage everything, and I can actually open a file, and before opening a file, I know whose file it is. Not just linear algebra test. The PDF. Okay. Ramble finished. I will repeat it next time and the next time and the next time until the next test. Anyway, to make you start reading instructions. And until then, yes.
The magnitude of AB is 64 because the 9.
Well, in which 64?
Last one.
The 9 is 3 square.
Magnitude of A vector plus B vector.
Okay. A plus B. So we had okay, it's 9, it's not 9 square, of course, because I was looking at 3, I was thinking 3 square, and I already, yes, you are right. This is just 9, not 9 square. This is just 9, okay, just 9. So it's actually 13 plus 49, that is 62, in fact. So it's 62 under the root. Okay. All right, so let's finish for today, and I'll see you on Wednesday. On Wednesday, as I said, lots and lots of exercises and examples, both in geometrical form and in coordinate form.
Yes, ma'am. Ma'am, I send you.
One by one, please.
Ma'am, I send you a mail for the lecture recording link.
Okay, you have to email, and then I send the email as a reply. Yes, because as it is, it's not ready for today's lecture.
Last week.
For last week from Wednesday, probably.
No,
okay.
No, for the first week. The first week.
Past week, yes. Just if you tell me the dates exactly in your email, I will send you the exact file you need. Okay.
I did send you a mail.
Okay.
Miss, can you tell when will be the retest? You said
The retest will be when I can make it. At the moment, not this week.
there will be
Maybe
a
next week and maybe the week after that. Definitely not this week. Definitely not this week.
And the results,
for the
when
matrix
we
test.
can.
The results will be when I finish marking. Marking online is actually very difficult, especially if your files are poor quality, if I can barely read them on my screen. So some of the files are very poor quality, I already saw. So some people have sent me very dark, very foggy, hazy, out of focus pictures. So it will take a lot of time because my eyes cannot take that much. It will be some time. As soon as they are ready, you will see the marks in Ortus. You know that Ortus gives you grades. I will enter the grades in Ortus and you will see them as soon as they are ready. They will be visible in Ortus. In the grade.
Okay, thank you.
Mm-hmm.
Ms. Shevchenko?
Yes.
I have a question about the cameras. You said
Yes.
that on the exam we have to show our face. And
Yes,
our
yes,
hand.
yes. I know it's not a simple thing. I have tried it myself, but it's doable. It's actually doable. It takes time. Of course, you cannot do it in the last minute before the test.